Uh, okay, so I just want to do a correction from last time to start. Last time, I believe I said that inflection points appear when the derivative is zero and the second derivative is zero and the sign changes, but the second derivative can also not exist, and the sign changes is also valid for an inflection point. So, and we'll do an example of where that occurs. Yeah, by the way, just make sure you're muted. I think I heard some background noises. Okay, so how do you find inflection points? Let's do one that's a bit interesting, like x, absolute value of x. How do you find the inflection points here? So first, we need to look at the second derivative, right? How do you deal with absolute value? What is x absolute value of x? How do you find the derivative? So just want to make sure, can people hear me, and can you see the screen? Okay, great. Yeah, so how do you deal with the absolute value? Remember how to deal with that? What is absolute value of x? Can someone tell me what absolute value of x is? It's a piecewise function. Something happens at 0. What is absolute value of x when x is negative? Or maybe a little bit quiet today, that's fine. It's negative x, if you remember. Right? If you plug in a negative number into absolute value of x, it negates it, makes it positive. Okay, good. Yeah. And then what is it when x is positive? It's just x, right? It doesn't change. You plug in like positive 3, for example, you output positive 3. So what is x absolute value of x? Well, it's negative x squared when x is less than 0, and x squared when x is greater than or equal to 0. Okay, what's the derivative? What's the derivative when x is less than 0? Can someone tell me that? Yeah, it's negative 2x. How about when x is greater than 0? Two x. Okay, now, why don't I include equals to 0? What's going on at 0 that I might have to worry about? Someone has their mic on, so if you can mute yourself. Now I can mute for you. Anybody know the problem with 0? It's not a problem for the first derivative, but remember that the derivative is a limit. So at 0, right, there's two things going on. There's the left-hand part and there's the right-hand part. So we need the definition of the derivative here. Okay, so then we get absolute value of x. So the derivative is 0 here. Do you see why we need that? Because normally when we do the derivative, right, we have to look at the, when we first started the derivative as a limit, at 0 there's something weird going on, right? From the left of 0, it looks like this function, but to the right of 0, it looks like this function. So when dealing with piecewise functions, you may need to use the definition of the derivative. Okay. Okay, so now let's look at the second derivative. Okay, what's the derivative when x is less than 0? Look at the second derivative now. -2. Now what's the derivative when x is greater than 0? 2. Now what's the second derivative when x is equal to 0? Yes, d and e. And to show that, let's use the definition of the derivative again. So let's just, because this is a weird function. So we know the derivative at 0 is 0. We showed that. So it's the limit, of course. Now there's two things that happen. When x is less than 0, the derivative is -2x. So divide that by x, and you get -2. So that's precisely what we have here. When you look at x bigger than 0, you get 2x, and then divide by x, and you get 2. So the limits don't agree. Left does not equal right. However, this is still an inflection point, right? Because the second derivative does change sign here. And this point does exist on the graph, right? X, absolute value of x, you plug in 0, that is a point, right? But it's not a point in the second derivative. So this is an inflection point. Okay, so any questions about that? Yeah, so I just wanted to clear that up. I said inflection points are when the second derivative is 0 and the change is sign, but it can also not exist as long as it changes sign. Okay, so by the way, what does this graph look like? It's the parabola on this side, and then it's a parabola on this side. -x squared. Okay, so any questions on that example? You have one in the homework that's similar, so I also wanted to do it for that reason. Okay, so we're just do a lot of problems today. Let's find the concavity and inflection points of this function here. Okay, so what do you need for concavity? What do you need to find? And inflection points? What is used for concavity? Yes, second derivative. Okay, so let's find it. F prime of x is cosine minus sine. And then f double prime of x is equal to negative sine and then minus cosine. Okay, so the question is, when is the second derivative 0 and when does the second derivative not exist? How do you determine this? Well, first of all, does the second derivative ever not exist? Does this function ever not exist for some x? No, so we don't really care about this part. So let's set it equal to 0. All right, so one thing you can do is just factor out by the negative. Okay, so how do you solve this? When is 0 equal to sine plus cosine? And I'll give you a hint. Let me write it this way. Good, yeah. But one of them is negative, right? When is sine equal to negative cosine? Okay, and here's a little trick when dealing with this. What values are sine of the angle? How do you determine sine? On the unit circle, what are you looking at for sine? I mean, are they the x or y values? When you take sine of an angle, do you look at the x value or the y value? The y value. We look at cosine, so that means it's the x value. So I want to find all angles such that the y value is equal to negative of the x value. However, that's nice, right? That's just y equals negative x. So what are the angles that make this true? It's wherever the line y equals negative x intersects with the circle. So at this point here and this point here. So that can help you kind of visually see where these are. Do you know what that angle is? Or these both angles are? This one is pi over 4. That's where y is equal to x. So it's the negative one. So on the opposite side. And this one's pi over 4. It's one of the over 4s, right? It's the other one. It's 3 pi over 4. This one is 7 pi over 4. So those are the angles. And since we were on 0 to 2 pi, it's only those two angles. All right, any questions about that? All right, one thing you could do, which is probably a bit too complicated, but maybe this was your first thought. X equals arc sine of negative cosine of x. Which you probably actually never, let's just not even entertain that. You could do something like that, but I don't think it would be helpful. All right, but this is fine. All right, so these are where the second derivative is 0. So let's look at 0 to 2 pi, and then let's look at our points 3 pi over 4 and 7 pi over 4. So we want to find where the function changes from positive to negative, or negative to positive possibly. Okay, so let's remind ourselves what our second derivative is. Okay, here's something to be careful about. Don't use this expression when plugging in numbers, because what we did here was we factored out by -1. You need to use the expression before setting things equal to 0. So we use this for test values. Because you might do some things to make it look nicer here. And don't use this. Does that make sense why? But when you do a test value here, you're going to get a number, but what it actually is in the derivative, it's negative of that. Right? This is the second derivative. Okay. Okay, let's do some test values. What's a good test value here? We don't want to use 0 because that's, we want to look at like the open interval, right? Not including 0. So do something in between. Because we don't know maybe what's happening over here. Yeah, pi over 2 is good. Alternatively, you could just look at it. You know that at least in this quadrant, sine and cosine are positive. So that could tell you right away. But also using pi over 2, you know that sine of pi over 2 is 1 and cosine is 0. So this is negative over here. Okay, what's a good test value here? And then what's what's a test value, and then what's a quadrant example? So now let's look at the next interval. Pi, yeah. So when you plug in pi, you get negative. So sine of pi is 0. Cosine is -1. So this actually makes positive. Okay, here's the quadrant trick. You notice in this quadrant, both sine and cosine are negative. So when you add them, it's negative. Okay, now this is a bit harder one. I mean, there is an angle in between there. What's the nice angle in between 7 pi over 4 and 2 pi? It's like this angle here. Yeah, 11 pi over 6. So sine of 11 pi over 6 is what? Do you remember? If you kind of look at it, you can kind of figure it out or guess. What do you think it is? Yeah, negative 1/2. And then what is cosine of 11 pi over 6? Yeah, root 3 over 2. Which is bigger, root 3 over 2 or 1/2? So is this positive or negative, this sum here? Yes, it's positive. So that means the whole thing is negative. Yeah, so with the negative sign, that makes it negative. Okay, if you don't like doing 11 pi over 6, another trick just by intuition is the pi over 4 angles, anything over 4, is the turning point where the absolute values of sine and cosine change from which is bigger, which is smaller. So in this little region here, which is bigger, absolute value of sine or absolute value of cosine? Yeah. So then it flips on this side. So now sine is bigger. And then over here, cosine is bigger. Absolute value. And similarly over here, sine is bigger. So that means over here, cosine is bigger. So it's a little trick, right? If the cosine absolute value is bigger than the sine absolute value, so you know that cosine is positive and sine is negative in this fourth quadrant, that means this has to be positive. So just a trick, and like if maybe the turning point in question maybe was 11 pi over 6, what would you do for this little region here? Then you can do that trick, where you don't actually have to think about an angle in between, but you can kind of just know which is bigger based on where it is on the unit circle. Anyway, so what are my inflection points, if any? Yes. At 3 pi over 4 and 7 pi over 4, the second derivative changes sign. So those are the inflection points. So now depending on what the website likes, the homework website, the point itself they might want as a coordinate, because that's literally the point where it inflects. So just remember that you plug it into the f value if you want the actual coordinate. Okay. Questions about this one? It's a little trig. All right. Let's do another one. Okay, let's practice first derivative test. And we'll think about the second derivative test as well. But one might be harder than the other. Okay. All right, so how do you find the local maxes and mins of a function? What's your first step? What do you do first when trying to find a local max and min? Yes, find derivative. What rule do we need to use for the derivative here? I assume you all know it because we just had the quiz on it. It's the quotient rule. Good, yeah. So it's going to be 1 x squared plus 4 minus 2x then times x. And this is over x squared plus 4 squared. Let's clean this up a bit. We get x squared plus 4. X squared. All right, yeah. So we have an x squared and we have a minus 2x squared. So this makes negative x squared plus 4. Almost factorable, but not quite. Okay, well, can we factor this? Can we make this a little easier to look at? I'll give you a hint. I'll rewrite the numerator. Other way around, though, it is different. It's going to be 2 plus x and 2 minus x. Okay, what you wrote is the negative of that, right? Because the 4 is first here. But you have the right idea. Okay, so let's talk about first and second derivative test. What do you think is easier, using the first derivative test or the second derivative test? So using the first derivative test, we go right to the critical numbers and draw a number line for maxes and mins. For the second derivative test, we need to find the second derivative and then plug in critical points. Yeah, this is going to be a hard second derivative to find. Not impossible, but I mean, we'll do it for the practice, but in practice it's a little bit harder to do. So let's just use the first derivative test. What are the critical points? Yes, 2 and negative 2. Is the derivative ever not exist? No, why not? What are you looking at to say why it does exist everywhere? Good, yeah. The denominator is always positive. And not equal to 0, most importantly. Sorry, a little laggy today. Yeah, I like that too, because it's an even polynomial with a constant, so that also is a reason why it's always positive. Okay, cool. So we only have to worry about these 2 points. Okay, by the way, if so the denominator is always positive, right? So when we do our test values, we don't really care about the denominator. Do you see why? All we really need to do is plug things into the numerator. Right? Because no matter what you plug in, it's always going to be positive, so why bother? Okay, so someone give me a test value, or let's not even use test values, let's just kind of intuitively look at it. Plug in something that's less than -2. Is this thing going to be positive or negative? Is the first factor positive or negative when you plug something less than -2? Positive, right? In fact, if you plug in anything that's negative, you'll get a positive number. Okay, how about here? When you plug something less than -2, what do you get? Negative. So positive times negative makes negative. Okay, so now plug in 0. That's probably easier. Plug in 0, they're both positive. Okay, so now let's do the other one. Plug something bigger than 2. What is it in the first factor? Negative. And then obviously it's positive in the second factor. Okay, so there is a change in sign. So at x equals -2, f of -2 is it a max or a min? The derivative changes from negative to positive. Does that mean it's a max or a min? Good, a min. All right, and if you ever forget the rule, just kind of draw a picture. Negative derivative to positive derivative, that looks small. Okay, and then similarly, going from a positive derivative to a negative derivative is a max. Okay, so questions on using the first derivative test? Okay, so for the sake of argument, just to see why the first derivative test is nice in this case, let's just try the second derivative test. So I'm going to write out the first derivative. Oh, by the way, just want to make very clear. If you factored out -1 here to make it look nicer, and then when you were setting equal to 0, you divide it by the negative, these would flip, and then you would get a flip of max and min. So that's why I recommend don't set things equal to 0 immediately. You'll try to make it as nice as possible first. All right, so I'm going to write out this first derivative. And then let's look at the second derivative. Okay, so it's going to be -2x and then x squared plus 4. And then minus, and then the derivative of this is 2 by the chain rule, x squared plus 4. Then times 2x by the chain rule. And then times 4 minus x squared. And this is all divided by x squared plus 4. What's the power of the denominator? X squared plus 4 to what? It's the fourth power, right? Okay, can you simplify this? should you go right to expanding it, or should you simplify first? How can you simplify this expression before expanding all this and giving yourself a headache? Good, yeah, you have an x squared plus 4 here. You have two of them, so watch out. X squared plus 4 and an x squared plus 4. So when you simplify this, get negative 2x. So that's nice, you don't have to FOIL. X squared plus 4, and then minus, and this gets taken out, so it's 4x, 4 minus x squared, then divided by x squared plus 4 to the third. Can you simplify further? It might just help. It's not too necessary, but it might help with the amount of work you need to do. Can you further factor the numerator? Yeah, in fact, I can even do better and factor out negative 2x. And that's why, so I don't have to FOIL on the first component. And then I get positive. Okay, so now there's not much I have to distribute. I have x squared plus 4 plus 8 minus 2x squared over x squared plus 4 cubed. So you can see immediately why sometimes the second derivative test is not that fun. But you would still need the second derivative if the question asked for like inflection points and stuff. So don't completely write it off. Okay, so that's the second derivative. Okay, so any questions on that? Okay, so what were our points again? Our critical points, 2 and negative 2. Okay, so again, notice that the denominator is always positive, right? So we don't care about that. Okay, so when you plug in 2, is the first factor positive or negative? So first factor, I mean the negative 2x part. Now it's kind of obviously negative. Yeah, good. And then when you plug in 2, this is positive. So the second derivative is negative at 2. So that means it's concave down, which is a max. Now let's plug in negative 2. When you plug in negative 2, the first factor becomes positive. When we plug it in here, it's also positive. So it's a min. All right, is that what we had before? Does it agree with the first derivative test? F of negative 2 is min and f of 2 is max. Yes. So f of this was -2. All right, so questions on the first derivative test? Oh, we could. So notice that while we're here, let's just try to see what the inflection points are. All right. How do you find inflection points? Yeah. So is the second derivative ever not exist? No. It's never d and e. By inspection, since we factored it nicely here, you can see immediately where the second derivative is 0. Where are those points? There should be 3 points. Good, yeah, 0, then square root 12. That's setting the second factor to 0. And then whenever you square root, you always do the minus. Okay. So here's, what is square root 12? It's 2 root 3. Is that right? Yeah, 2 root 3. So -2 root 3, 0, and 2 root 3. Okay, so when dealing with radicals, all you have to know is, can you find a number that's nice that is, bigger or smaller? Is root 3 bigger or less than 1? Bigger, right. So that means 2 is a valid test. 2 is a test. So don't be afraid of the radical, because all you're doing is a test values. And similarly, -2 is a test. Well, you don't even need 2. You could just 1 is fine, right? So 1 is a test, and -1 is a test. And then what's a number that's guaranteed bigger? Sure, yeah, 4. 4, -4. Right, radical 3 is less than 2, so you can just round up to 4. Okay, so let's do the test values. Okay, let's plug in 1. In the first factor, it's negative. In the second factor, it's positive. Plug in -1, you get a positive and a positive. So boom, we already have an inflection point. So 0 is an inflection point. Okay, how about when you plug in -4, you get a positive. And now what happens here when you plug in -4? In the second factor. And remember, I'm ignoring the denominator, right? Because it's always positive, so who cares? When you plug in -4 here, in -x squared plus 12, do you get a positive or a negative number? Yes, a negative. Yeah, be careful. Don't. Yeah, that's not negative, right? So, yeah, the x squared of x squared times -4 squared is positive 16, then negated, plus 12 is negative. Okay, and then over here, it's positive, and then it's negative. Okay, so what are inflection points? Oh, I'm sorry. The first factor is negative, right? Negative 2 times 4 is negative. Okay, where are the inflection points? So really, the question is any of them not an inflection point? Yeah, they're all inflection points. And again, why is because the concavity always changes. Okay, so this is so I think that's probably a good strategy is that like if you have to find the if the question wants you to find the max and min and the inflection points and stuff, you might as well just go right to the second derivative test because you need to do that anyway. Yeah, but if the question only asks for max and min, depending on the function, right? Maybe it's hard to factor, and test values might be hard to do, where the second derivative might be better. But when it's easily factorable and easy to plug in, then the first derivative test is probably better. But again, like a question like this, where the second derivative was a bit complicated, right? You may not want to do that. Maybe the first derivative test is better. Okay, so questions on this? So this is stuff we did last time. Some more examples. Okay, so for this class and probably next class, we're going to talk about curve sketching. So what info do you get from derivatives to help graph? Now, someone tell me in the pre-calc, so if you did not know anything about calculus or anything before this class, how did you curve sketch? Someone tell me some methods you use to curve sketch. Like what were some what some sort of information did you need? And then we'll see how calculus is giving us more info. Yeah, zero value, so like x-intercepts. We can do that without calculus. How else? Yeah, what else? Yeah, sure, end behavior, and we're gonna call it different in calculus. What's end behavior in calculus? Do you remember what we used for end behavior in calculus? Yeah, there's a limit to plus or minus infinity. So this allows us, using this allows us to give end behavior for some more complicated ones that we couldn't use pre-calc methods. All right, what else do we have from pre-calc? How about like asymptotes? Um, how about vertical asymptotes? How do you find vertical asymptotes? And we have a calc version. What's what's a vertical asymptote in calc? Not where the derivative d and e. That's like this is the derivative not exist, but that's not a vertical asymptote. But it's a different type of d and e. But not about the derivative. Yeah, it's a limit. And what particular type of d and e is it? Not all d and e's are vertical asymptotes. It has to be infinite, right? Or for example, let's go with this one. This limit d and e, but it's not a vertical asymptote. So d and e in the sense of infinity. Okay, how about horizontal asymptotes? Oh, so for pre-calc, it's denominator to 0 after factoring, after canceling. All right, how do you find horizontal asymptotes? The pre-calc or calc method? This kind of falls under end behavior. All right, when you look at the limit as x goes to infinity, if it's equal to something, then it's a horizontal asymptote. Okay. Any other asymptotes? Do you remember another asymptote out there? There's one other kind of asymptote, which we didn't talk much in this class, but maybe we will now. What's the third type of asymptote that there is? Hyperbola kind of looks like this type of asymptote, but it's not only for hyperbolas. Yeah, we call them, some people call them slant asymptotes. And it's exactly how you talk about it. It's if the limit as x goes to infinity looks like a line, ax plus b. So this is usually used in rational functions. We might see other types of functions that have slant asymptotes. Okay, I'll just add y-intercepts here since no one said it. All right. And I might add, yeah, what are some other things? Do you remember? From pre-calc. Domain is helpful. Right, you want to know where the function exists. And do you remember the one other one that was helpful? It's about like if a function kind of looks the same about an axis, then you have less work to do. Symmetry, yeah, that was the last one. Okay, does everyone remember what symmetry is? There was two types, right? Even and odd. Someone tell me what even is, and then someone tell me what odd is. Or whichever you remember. Always the hint with it, it's yeah. Even is mirrored over the y-axis. So you always look at what happens when you plug in, right, the similar point across the y-axis, or same x value. So what happens when you plug in negative x? What should it be for an even axis? What does it mean to be mirrored over the y-axis? What should, when you plug in the negative, what should your y value be? Yeah, it should be the same as when you plug in the positive. So which one is odd? First of all, what's the symmetry, and then what's the formula? What are odd symmetric reflective over or mirrored over? It doesn't have to be reflective over the x and y axis, but it's a kind of the weird one. It's here, I'll draw it, and then so the idea is that if you have a point here and you draw a straight line to the origin of some length, you keep on drawing of that length, and then f of negative x is over here. So actually, it's reflective over the origin. It's negative x. All right, yeah, so questions about that? All right, so that was symmetry. So this is symmetry. So if you draw a line to the y-axis of some length, you keep on drawing of that length, and you end up on the curve. So for example, like this would something like it would be origin symmetric. It's reflective over the origin. Okay, so let's take a break, and I have kind of half of 4, and then down is all calculus. This is kind of a rough sketch of what we talked about before. All right, so let's meet back at 6:40. And then we're actually going to sketch some functions. All right, but in the meantime, if you want to ask me questions, it's fine. All right, so first, curve sketching. This is going to be probably a good guide for all the information. So the first couple are things that you should know from pre-calc. Let's just make sure. How do you find x-intercepts? What do you set equal to 0? Yeah, you set y equal to 0, and then when you do for y-intercept, it's the other one, x equals 0. So for symmetry, plug in negative x, not a number, Please do not plug in a number. Symmetry means it's true for all x, so you can't plug in a specific number. All right. So, and then all these things that we know. So let's just do an example and see how this works. Okay, so we're going to sketch this rational function here. So this might be a function that you could sketch in pre-calc, but we're just going to do it again as a little review. All right, so our first guide was looking at the domain. That should be helpful, right? You want to know where you can graph things and where can't you graph things. What's the domain here? What's the domain of this function? Yes, everything. Right, and why is that? It's because x squared plus 1 is never equal to 0. Okay, let's do b. What was b? X and y intercepts. Okay, so let's do x-intercept. A y-intercept is easier, right? In general. Y-intercept. What's the y-intercept? Remember, there's only one y-intercept, but there could be many x-intercepts. What's the y-intercept? So it's always something comma 0. Sorry, other way around. It's always 0 comma something. Yeah, 0, 0. And then what's the x-intercept? Or many. Also 0, 0. Do you remember what's the multiplicity of an x-intercept? Sometimes this doesn't matter. What's the multiplicity of the x-intercept? Right, the power of the factor, yeah. Multiplicity 3. Okay, do you remember what multiplicity tells you, by the way? Yeah, so if the multiplicity is odd, what does that tell you about the shape? So really, it's asking, like, what happens at the x-intercept? There's two things that can happen at the x-intercept. Could either touch it and then go away, or it can cross it into the other half of the plane. Or bounce, yeah. So do you remember what happens when the multiplicity is odd? Passes through, yeah. If even, it would touch. Okay. What was C? Symmetry. How do you find symmetry of this? What do you do? Good, yeah, you always plug in negative x. There's really always one step for symmetry. You just plug in negative x and see what happens. Right, so you want to see if either y stays the same or y is negated. Right? That's the other case that could happen. What is it here? Is this even or odd? Or neither? It's odd. So this is something I always like to do when determining even and odd. Always factor out negative. Factor a negative. Because what you want to see is what happens inside the factor. So it's odd. Okay, so that means we only have to graph half of the thing, and the rest just follows. Okay. Asymptotes. Are there vertical asymptotes? Does this have any vertical asymptotes? No. Does this have a horizontal asymptote? No. And why is that? Yeah, so let's go. So no vertical because domain. And then why no horizontal? For this one, you can give me 2 reasons. I don't mind a pre-calc reason for this one. Good, yeah, that's the pre-calc version. The degree of the numerator is bigger than the degree of the denominator. Do you remember how to determine this using the pre-calc version? Or the calc version? And again, for things that are not rational, we would need the calc version. What's the calc version? Take a limit as x goes to infinity of x cubed over x squared plus 1. And do you remember the method that we did when dealing with infinite limits of a rational function? There was one step that we did. Yeah. So if you factor out x squared, you get x. Well, how we did it was we factored it out by just the highest power in general. So which was x cubed. Get 1 over x, and then 1 over x squared. I believe that's how we did it, right? And then 1 over 0 plus 0, and then that's, who knows, that's d and e. Yeah. Okay, so there's no horizontal asymptotes. Is there a slant asymptote? Do you remember how to determine if a slant asymptote exists? I'll give it away. The answer is yes. Do you know why? by inspection. Something to do with the degree of the numerator and the degree of the denominator. So if the degree of the numerator is 1 more than the degree of the denominator, then there is a slant asymptote. All right, does anyone remember how to find the slant asymptote? No? Here's what you do. You polynomial divide. And then the remainder is the slant asymptote. Sorry, the stuff that's not remainder is slant asymptote. The quotient. Quotient, not remainder. Is the slant. Okay, do you remember how to polynomial divide? How do you divide? What goes here? Yes, x. You take the highest power coefficient, or highest power term, divide it into x cubed, and then the result is x. And then what do you do next? So what goes here? You also multiply by x squared. So it's x cubed and then plus x. So there's no x squared term. And then what do you do next? Subtract, yes. And always be careful with subtraction. I always like to draw up a little parentheses because although this term cancels, but this term is actually negative x. Okay, what do you do with the negative x plus 1? What is negative x plus 1? Do you continue? That's the remainder. So what is the quotient? It's x plus, we can turn this into 1 minus x divided by x squared plus 1. So this is equal to x cubed divided by x squared plus 1. Okay, so why is it the slant? Let's use calculus. Why is this a slant asymptote? Think about limits. Think about the limit as this goes to infinity. What's the limit? You have the limit there? Oh, I'm sorry, there is no plus 1. I don't know why I put a plus 1. It's negative x. What's the limit of negative x over x squared plus 1 as x goes to infinity? If not that, what's the horizontal asymptote? Not D and E. Look at the powers. So I'm only looking at this term, not the whole thing. It's the horizontal asymptote of that, of negative x over x squared plus 1. It's 0, yeah. So notice as x goes to infinity, this term is like becoming nothing, right? And then what's left over is this slant asymptote. So that means that as this thing goes to infinity, it's beginning to look more and more and more like a flat line, right? Because this extra term just becomes like garbage. And then the only term that's left over is like x, right? The function looks more and more like a straight line because this stuff that makes it not a straight line just goes to 0. So maybe like something down here too. Okay, so that's the slant asymptote. So when we draw our graph, we're going to have a slant asymptote at y equals x. Okay, any questions about that? So slant asymptotes exist for rational functions at least when the degree of the numerator is equal to the degree of the denominator plus 1. Okay. What's next? So that takes care of asymptotes. So now let's do increasing and decreasing. And we can throw in local max and min here because we can use that. Okay, how do you find increasing, decreasing, local max, and local min? Yeah, first derivative. Okay, so first derivative of this, use the quotient rule. You can get 3x squared, x squared plus 1, minus 2x times x cubed over x squared plus 1 squared. Okay, can you factor anything out to make it nicer? Like before distributing? I don't know, it's not very necessary, but I like to do it. We don't have to. 3x to the fourth plus 3x squared minus 2x to the fourth. Okay, so that's x to the fourth plus 3x squared over x squared plus 1 squared. Okay, now how do you factor this? How do you factor the numerator? Yeah, take out the x squared. You get x squared times x squared plus 3, and then x squared plus 1 squared. Okay, so what are your critical points? Just 0. Right? The the denominator is never 0, so there's no problem with derivative not existing. And this term is never 0 because its factors are like have I in it. It's I root 3. Okay, so that's nice. We only have one thing to test. Okay, let's think of, so having at 0, it's nice. All you just think is positive and negative. Actually, you can probably look at this and tell, you can see immediately what it should be. What do you think it is? Is this positive or negative? Forget about the testing, just kind of look at the function. Yeah, it's positive on both sides, right? Why do you think? Yeah, everything's squared, even. You're not subtracting anything. Yeah, so what does this imply about maxes and mins? Since this is 2 plus, yeah, you can just say no max, no min. No max and no min. In fact, it's always increasing. All right, cool. So what was another one we had in our list? Concavity. All right, let's find the second derivative of this thing. I'm going to write the first derivative out. X to the fourth plus 3x squared. Yep, 3x squared over x squared plus 1 squared. Okay, let's find the derivative of this. Okay, so product rule. So 4x to the third plus 6x, and then x squared plus 1 squared minus 2x squared plus 1, 2x, and then 4x to the fourth plus 3x squared. All right, it's all over x squared plus 1 to the fourth. All right, how do you simplify this? Yeah, there's all these x squared plus 1s, so get rid of them. So, and while we're here, is there anything else that we can do? Maybe in the individual factors? So look at this one, and look at, well, this one. There's 2x in both of them. So we have 2x squared plus 3x, x squared plus 1, minus 2 times x to the fourth plus 3x squared. 3, yes, not 3x. Thank you. It's all over x squared plus 1 cubed. Okay, so let's simplify. Okay, so this is 2x to the fourth plus 2x squared plus 3x squared plus 3 minus 2x to the fourth. That's nice, minus 6x squared. So you have a 2x to the fourth and a minus 2x to the fourth. This gives you 5x squared, and then minus 6x squared is x squared, and then you have a 3 left over. Okay, so you have 2x. What did we say? Negative x squared plus 3. So actually simplified kind of nice. Okay, any disputes on my distribution? All right. Okay, so what do we do for second derivative? We're trying to find the concavity. So what are the nice points? What are the points that we're looking at? Yeah, square root 3 and negative square root 3, and then there's one other point. I'm sorry, I put a 3 here. It's squared, right? And also 0 from this one. By the way, there you could write this if you wanted to for factoring purposes as root 3 plus x root 3 minus x as a difference of two squares. So that might be easier to factor, but it may not look as nice. So depending on what you like. If you like the factor version where all they do is plus or minus, maybe it's harder here. Up to you. Great, so give me some test values. So always important when you have a radical, you have to determine, kind of where it lies on the number line. So 1 is before radical 3, right? So that's a good test value. All right, so when you plug in 1, notice the denominator is always positive, so who cares about that? You're going to have a plus, and what's the term here? It's positive. So it's positive on this little region here. We plug in negative 1, you get a negative and a positive, so it's negative. Okay, what's a nice number after 3? After radical 3? Yeah, 2, 3, 4, whichever works. Sometimes I like to go big, yeah, you can do 4. Okay, so you have a plus, and then you have a minus. Over here you have a minus, and then a minus. So let's make a plus. All right. So where is it concave down? What's concave down mean? I mean, down like negative. So it's negative, yeah, negative square root 3 and 0, and then also on the right-hand side. Okay, and then where is it concave up? Everywhere else, it's negative infinity over here to negative root 3. And then union 0 to root 3. Okay, what are inflection points, if any? Yes, since it changes sign at all the points, they're all inflection points. All right, so for the remainder of class, let's graph this. All right, so let's zoom out a bit. We'll do more next time. All right, so let's start with our preliminary stuff. Okay, x and y intercept are 0, 0. So let's draw a point spot there. We have odd symmetry, so we only really care about one side of the graph. And we have a slant asymptote. Okay, so let's draw a dotted line on y equals x. Let's see, what else do we do? Okay, that was the slant asymptote. We saw it's increasing and decreasing everywhere. Or sorry, it's increasing everywhere, and there's no max and min. And then we have these inflection points at negative root 3, 0, and 3. I'm going to go out a little bit. Negative root 3, and then root 3. All right, so it's concave down from negative 3 to 0. So it's down here. So it's up, down, up, down. Okay, so concave up has kind of this shape. Concave down has this shape, and this shape. So if you want to sketch it, so at the slant asymptote, it's coming into the slant, and it's kind of hard to see the concave up. Actually, we should probably plug in the points from the inflection points just to see where these happen. Okay, so negative root 3 and root 3. So f of negative root 3 and f of root 3. So remember the function was, where f of x is equal to x cubed over x squared plus 1. Was that it? Yes. Okay, so when you plug in root 3, you get 4 in the denominator, and then you get root 3 cubed. Okay, and then when you plug in negative, you get negative root 3 cubed. Actually, we can call this square root of 27 over 4, right? That's probably nicer. which is 3 root 3 over 4. And then we'll have negative 3 root 3 over 4. Okay, so where does this point lie around? It's less than. Is this bigger than 1? Yeah, it's okay. So I like to look at the square. 3 root 3 over 4 squared. What is that? 9 times 3 is 27 over 16. So this thing is bigger than 1. All right, so let's say this is 1. It's somewhere like around here. Let's call that the point. If it's bigger than, yeah, let's call it somewhere. Okay, so it's going to be concave up until this point at root 3. After which it turns into concave down and then hits the asymptote. So now at this point, we know it's odd symmetric, so we just need to copy this graph on the other side. So it's going to be concave down towards negative 3 and then turn around and be concave up towards the asymptote. So here's the concave down part. Notice that the tangents are above. And then here is the concave up part. And notice the tangents are below. Okay. All right. So any questions about that? In fact, I'll plug this into the computer and see if we were close. So the biggest thing, we didn't have much information aside from the concavity. So do you see how that helps? Yeah, so it's hard to see. It's unfortunate. Yeah, if you plug this into the calculator, it doesn't show where the concavity flips, so it's not very helpful. Anyway, so that's all we have for today. But next time we're gonna do one with trig and see how that plays a role. Yeah. So it's not much new today, but we've done the second derivative test, so it's just kind of applying all these tests that we went over last time. But we're gonna do more next time. All right, so you can head out now. We're done. But you can stick around for questions if you have them.